Alright, so we are doing Codeforces Round today. And it already started, I believe, so I'm going to open the problems, please. Yeah, the usual load at the start of the contest. Okay, so this is by Ukrainian author that I didn't know before, but I believe that he was an IMO competitor when he was in high school. So that's going to be pretty interesting, I hope. Okay. So we have to arrange some numbers on the cycle, right? So why doesn't it work like this? We go for n equals 3, for example. We go let's see, 1 2 to the opposite, 3 4 and 5 6. So we have 9 and 11. Yes, because as we go from, for example, these and numbers to these and numbers, the only number that changes is this pair. But here we have 11, and that's a problem, right? Because any of the numbers should differ by at most one. So we have to like alternate something like so we have to go like 4 3 and then 5 6 again, so that now we have, instead of so now we have 10 here, 11 here, then 10 here again, and 11, 10, 11. So I believe that works, right? So that should be pretty easy to code. And then the tests are easy to run as well, right? Okay. What is it? Oh, okay. Let's double check. That I'm sorry. Okay, so for that is so for odd n that works. Okay. For even n that doesn't work. But for even n, we can do something. Wait. Why doesn't it work again? How exactly my construction is supposed to go? here, 3, 4, 6, 7, 8. So as we go here, we get a +1. We go like that. We get -1. We write down this nice thing. I'm not sure. Not sure why it doesn't work. Okay. So +1, then -1, then -1 again. Okay. So we have to. Yeah, why? Okay, so +1, then -1, then +1, then -1. Oh, and then -1. Okay. Yeah. So as we go to the opposite side, that's a problem. Right? We'll fix that. I don't know. Let's try that. Hello? Okay. No, I want to erase everything. Yep. Oh, sometimes there is a no. Sometimes there is a no. Okay. So we know that the answer always works. Probably if n is odd, at least for 3, right? 5, it doesn't work again. Okay. So let's see. So we want to have like +1, -1, -1, +1, -1 in this, in even case. So that is equal to this number different minus the opposite number, right? Okay. Something like that. So why doesn't this work again? 3, 4, and then 6, 5, for instance. That's kind of what I did, wasn't it? For 3, yes. But for 5, it doesn't work again. That's kind of exactly what I did, isn't it? Okay. Okay, so I don't know what it was. Okay, so in the even case, why can't we have that? So we have to have -1, +1, -1, +1. Oh yes, so that wouldn't work because these opposite difference have to be like opposites of each other, because this is the difference between elements. So that doesn't work. Okay. It's nice. So that was something a little bit slow, but that's alright. Like that, I guess. There's no way only 1 minute have passed, right? There's a queue. Okay, let's go to the next problem. Yep. Come on. Okay, so 11 minutes passed already. That's pretty bad. Okay. So the shortest cycle on integers. Come on. On integers, where the numbers are connected, if they have a common bit, basically. There's a queue. Okay. Right. So if you have 3 integers with a common bit, then the answer is just 3. Otherwise, for each bit, there are at most 2 numbers that have this bit. And so what we can do is just we can just pass in this we can just go from one number to another, and that's it basically. So what that means is what does it mean? It's not going to be a lot of edges, basically. There are at most 60 edges in the graph. Yep. Come on. How are we going to find the shortest cycle in a graph with 60 edges? Okay. The very least you could just go with these lists. Come on. That's good. So shortest cycle in a very small graph. Do we want to construct the graph like like explicitly. Do we? I don't know. So we have to be careful because two numbers can have more than one common bit. So we want to have only one edge in this case. So now what? Can we just run a brute force? I don't know, can we? We could run a BFS. Yeah. Could run a BFS. How will that work exactly? And how do we deal with the path that just goes right back? And just in general, how do we deal with going back using the same edge? There are only 60 edges. How do we find the shortest cycle in this case? Can we just run through all cycles? No, there can be a lot of cycles, right? So if we just forbid to go back, yeah, I know. Let's think. I kind of want to run the like a brute force, but how exactly will it go? I'm stupid. Well, if we forbid to follow the same edge, then what's the cycle that we're going to find? Even if you go like through a loop and then try to go back, there still will be a shorter cycle. So we can construct a graph on the directed edges, and then just find the shortest cycle in that, I guess. Whatever. We're running a BFS. Without going back. And we can go with maps or whatever you want, because the graph is so small. So however do we return to the vertex V? Going to be cycle. Okay, so that's something. The infinity case. So 3 in this case, and in this case nothing. Yep. In this case 3 again. So it's like 3. This is the smallest case when we have 3. And if we wanted to have like a cycle of length like 5, for example, we would go about like this, and then 32 plus 1 is 32. So here the answer is like 6, I guess. Yep. And if we wanted to do 3 on that, we would have 34 here. It's going to be 5 now. No, it's 3. Okay. Yeah, whatever. I think that works. I think it should work. So yeah, that was a problem. Let's go to the next one. Hope it works. Okay, interactive problem. Nice. We have a grid. Okay. Wow, that's a large view. Okay. So we want to know the numbers, and there are only zeros and ones in the grid. This cell contains 1, and this cell contains 0. So what can we ask? It's 1 like that. So a pair of numbers, a pair of cells which are at least 2 away. Okay. If there's exists a path. I'm sorry. if there exists a path that is a palindrome. Well, okay, whatever you say, but it's odd, right? Okay, so what can we tell from this is, for instance, if we ask for these pair of cells, we are allowed to do that, right? If you ask for these pair of cells, then we know that we just know if they're equal or not, right? Because it doesn't matter what's in the middle. And so we know this is a 1, so we can determine all the cells in these positions with both coordinates odd. And there's still q, okay. At most n squared questions. Okay. So we know that. What do we do now? We can ask for these. Oh, we can also determine these, right? Yes, we know all these cells in these like black squares of checkerboard, basically. Okay, so how do we do that? We can also determine for all other cells, like white cells, which of them are equal, right? So there are only 2 possibilities now. Okay, but which one is that? Which one of the 2? Which one of the 2? Wait, but we can make a question like about an even length palindrome now. So okay, so if we take, for example, these 2, if they're equal, and these 2 are equal, then we can ask and determine everything. If they're different and these are different, then again we can ask and determine everything, because there is only one way this palindrome could happen. But if they're equal but these are not equal, then they can't be a palindrome. But what we need to find is, so we know that there is we know that these are different, right? So how do you use that? Know that these are different. Well, I guess we can think about it later and just write the code. Okay. So here's our read. And we don't know anything at the start, but we know that the corner cells are like this. Okay. So let's determine all the odd position cells. Actually, let's just we'll find it out. So this we don't know yet, but if this an odd cell, like that happens here in between these rows, what we can do is, oh, but there are like more cases. Okay, so let's do that. Okay, maybe not. We'll just try all of them. The first cell we can skip. This is just a basically. Are they numbered from 1? Yes, okay. And the order is like that. So we're asking about the previous cell that we know already, and we're answered either 1 or 0, where 1 means that there is a palindrome. Okay. So if it's 1, then they must be equal. So like that, it's just a formula, whatever. Okay, so we can sort of do the same with all the even numbered cells. Almost. Okay. So 2s and 3s are going to be different classes. One of which is 1 and one of which is 0, but we don't know yet. Yeah. Okay. Yeah, there seems to be a slight complication, but we'll figure it out. Just for consistency. So we are figuring out this. Okay, so do it again. But now we do it the other way around. Yep, that seems like something like what we want to do. And actually, let's save up this query because it seems to be important. So we've asked about every cell. So how many queries did we make? It's like n squared minus 3. So, okay. So now we have to determine which one of the cases. So which are 2s and which are 3s. Let's play with it. Except let's not do that because this is not needed anymore. So for this grid, for example, 1, 3 is supposed to be the horizontal. 0, 0 again, 3, 1. Why are you asking me this? This is better. Okay. So yes, 0, 0 again, 0 again. And about that cell you don't want to ask me. So 2, 1, 2, 3 is going to be 0. I'm sorry. 1, 2, 0 again, and 2, 1, 2, 3 is going to be a 1. So the same question was asked twice for some reason. What's going on now? Oh, we have to break here again. We could do that in one cycle, couldn't we? Anyway. So 0, 0, 0, 0, 0 again, it's 1. But you, oh yes. Okay, so what do we do now? What do we do now? We could try all. So n equals 3 is somewhat. What do we make of it? What do we make of it? How do we go? No, let's just check that it works. 0, 0, 0, 0, 0, and 1. But you still didn't ask me about that. Why didn't you ask me about 3? Whatever. That's stupid. Yep. Okay. Again, 0, 0, 0. 2, 1, 2, 3 is 0, 1, 2, 2, 3 is 1, 2, 2, 3 is 0 again, and then 2, 1 is 1. Okay, so that's nice. What do we do now? Well, we could try 2 cases. And then see if there's a pair that's different. Now what? Let's do this. No. That's confusing. Anyway. That's confusing as well. What can you do? So that should work, shouldn't it? Okay. probably. Yeah, I know. So let's plan this grid again. We have 0, we have 0, we have 0 again. T1, T3 is, let's suppose 0, 1 is 0 again. This is supposed to be 1. Can you please flash it? Let's try again. One, 1, 1, 3, 2. That's a 0, and that's not it, isn't it? So something's wrong. We don't compute this thing correctly. Or maybe I was just inconsistent. No. No. I was just stupid. B. Let's try again. Yeah, 0, 0, 0, 0, 0, 1. Okay. Let's try again. 0, 0, 0, 0, 0, 1. And then you don't find anything. That's a shame. 1, 2, 3, 3 is supposed to be. Yep. Well. Do it again. It's supposed to be what? 1. And you don't find anything. But we are sort of, that was the case. So we ask 1, 2, 3, 3. Yeah, so something wrong here. Do it again. final. Okay, so to that we answer 1, I guess. Yes, so okay, so what if the whole grid is ones except for the bottom left corner? How did that work? So we have a 1, we have a 1, we have a 1, we have a 1, I suppose. Yeah, as long as it doesn't concern 3, 3, it's 1. It's 1. It's 1. And it's 1. Cool. One question. Is x the number? Yes, okay. So I suppose that works. Let's try and submit that. Whatever. So it does take quite a bit of time to solve these problems, but let's see if it's okay. It's still a Q. Wow. Okay. So C is kind of solvable now. Let's take a look at D. Okay. Did we? Oh yes, we have to output that little tiny question mark. Little tiny question mark. Otherwise, seems okay. And wrong answer on the pretest one, I suppose, does not count like towards penalty, so we should be all right. So okay, let's look at D. We have a tree. We have to write okay. So it's seems fine. This pretest is kind of slow. I hope it's okay. Yes, it's okay. Alright. Nice. 2n or 2n squared over 9. Okay, so that worked. Yeah, okay. Ooh. Interesting. So how is that supposed to work? We're writing non-negative integers. Can we write zeros? I don't know. So what if the tree is like a star where everything is adjacent to a vertex? What's the number? What's the answer then? So let's figure it out first, because it seems like it's a hard case. Okay, so we have this bramble. So we want to have 1, we want to have 2. Now we have 3, so we can write 4. And then we have also 5 and 6, so we can write 7. We now have 8, 9, and 11. So we have 10. We have to have 10. Then and we have 11, 12. I'm not sure how that's supposed to work. Let's let's try something. Can we just do it greedily? So the smallest sum that's not representable this way is going to be, I don't know what, but let's leave that for a second. It does not seem to be a correct answer, I'm sorry. Sums of 1. It's probably just off by 1, so it doesn't matter too much. Oh yeah, so that doesn't work. So that fixed it. Okay, so we don't have 3, and that's a problem. So what we could do is we could write down all the like represent the number in binary, and then write down as half of the integers are going to be like all possible lower halves, and then we have all possible larger halves, and then we can comprise any number. So that's cool. Does it generalize a lot? not sure. That's a nice idea. That's a nice idea. So what we can do now is divide the tree into halves and then do this. How do we go about? But now we are going to have all possible. We're going to need to have. So what we're going to do is like. So the trick is in this case, we're going to say that all these edges contains all integers from 0 to tk minus 1 for some k, and then we have just multiples of 2k. 2 times 2k. Okay. And then we can choose for any number x, we can look at its binary representation and take this here and then take this here. So for an arbitrary tree, we could divide it into two halves basically, and then kind of try to do the same thing, except now we want for all paths to this new root, take all possible values. How exactly do we do that? Is it easy? It's probably easier, right? Because yeah, it's just a simple GFS, right? Yeah. The question is, how do we divide the tree? And that is, that's a good question. Oh, I see now. We just have to divide the tree so that this is like, I don't know. So the smallest part has to be of size at least n over 3. Right. From n over 3 to n over 2. And that should be fine. How do you do that? Can we just do it greedily? Probably not, right? In fact, we have rejudged the. I hope my solution is okay. Yeah, it's okay. Yeah, we can do it sort of greedily. Right. So we just take compute weights of the subtrees, and then so all the weights are less than n over 3 because we argue that as long as it's at least n over 3, then we can just take this subtree. So if this is true and we start hanging, then what happens, we attach subtrees one by one, and as long as we are in this interval, in fact we can go up to n over 3 just by symmetry. Yes, so anything in this interval is okay. And if we attach a new tree and we suddenly jump like that, then it means that it was large enough and we could just take it. Cool. That's pretty cool. Pretty cool problem. So let's write that down. Yeah, like this. we have to be sort of careful with all these rounding. Yeah. So we want the. So how do we put this rounding here? We want our subtree to be that, I guess, following this. This gap, right? And now we should be fine. I think so. Yeah, what we have to ensure is that if we attach a small subtree to a small subtree, we cannot get over here. So n over 3 plus n over 3 is at most to n over 3. It is correct. Am I stupid? Yeah, of course it's correct. Of course it's correct. Of course. Wait, is it? Is divisible by 3. Yeah, that's right. No, please don't. Please don't. Okay. Okay. Right. So again, you have to kind of be careful here to trigger this coloring in at the right moment. So sometimes we will just want to use 1. We want to do that. Don't think we actually care. And we also have to. Oh, we can rearrange the edges. That's nice. How about we just go like this? here. And check this one last time. Okay, so what does it mean? I guess. So that's supposed to do exactly what we want. So I'm not sure how do we get -1 here. I'm sorry. Just to be sure. Yes, somehow we do get -1 here. Is there a box on? So supposedly we just quit. That's right. Okay. Now, how do we have -1 here? That's not supposed to happen. How do we get this edge here? Oh yes. Oh yes. Exactly. Exactly. That's very good. Okay. So what if we have like this? We want to have something along the lines of 1, 2, and 3, 6 before. Yeah. 6 is enough. So now we can represent up to, well, we're supposed to represent up to 7. That's not very good, is it? Over 9, yes. Yes, that's good enough. Let's add some more. Yes. How is that 24? Don't really get it. How? I'm sorry. I don't suppose we run this thing twice. No. And then what? Eight is a lot. Where do we get 24? Okay, that's better. So yeah, 28. 28. Is it a lot? Yes. Okay. How do we do on the path here? Okay. Somehow 6. Oh yeah. This is not right. I guess that's better. Three, 2, 2. We don't really need that anymore. So I'm trying to check if it does exactly what it's supposed to do. Yes. Let's still work on this tree here. Okay, so I need to use multiple. Yep. What about some random tree, like binary? So we have this subtree of the subtree of the vertex 2. We're supposed to be 2, 4 is equal. Yes. So then we have 3 here. Let's draw it out. So we have this kind of tree. So we write 1, 2 here, and then multiples of 3 here. We have 3 here, 3 here again, so that we can have 6 here. We have 3 here, we get 9, and here we get 15. So we can get up to 15 plus 2, 17. Is that enough? Yes. And then we have this. But if n is equal to 1, we don't have to output anything. Can it even be equal to 1? Well, supposedly, if n is equal to 1, then we can just print nothing. And otherwise, do we have a lot of debug outputs? Let's also generate a random tree just for completeness sake. Like that, right? I'm guessing. Nope. Is this better? Yes, supposedly. Okay. We have 3, 3, 5, and then some multiples of stuff. And 3, 3, 5 is enough, probably. Yes, I suppose so. So let's admit that we don't have a lot of time. Maybe hopefully one problem. Is it D? No. If we solve D, is this D? Okay. Let's submit it. I didn't write a checker. Maybe I should have written a checker, but that's fine. Seems to work. That's cute. That's a cute problem. Wow. Kinda like it. It's interesting how you start to think about star being sort of the hardest task, and that hints you towards the solution. Like it. I like it a lot. Good problem. Good problem. Okay, combinatorics. So the number of these matching strings, right? Oh, yes, sort of different prefix functions. All right. So the expectation of stuff, right? The expectation of the square of this. So what we have to count is the number of. If you wanted to count the expectation, we could just count this. Consider all lengths, and then start matching corresponding symbols, corresponding characters, and then sort of count the equivalence classes. I'm sorry, I'll just try to figure it out on paper because it's not very convenient to draw on this thing. But yeah, maybe I'll get back to you when I finish this. Okay. So since we have to count the square, it's basically the expectation of number of pairs, right? And so this is equal to that, and also this is equal to that. Cool. So at the very least, this equal to this. Okay, so if you look at the largest of the two, the prefix and suffix, if they don't overlap, then we don't care. If they do overlap, however, then what do we have then? The prefix is equal to the suffix. So that gives us the period of the string. Okay, so I kind of get the general picture, but I'll have to think about it as I do. Sort of on my own. So I'll get back to you as soon as I can. I'll have to think this through a little bit. All right. Okay, so there's definitely some recurrence happening, but I cannot quite figure out the exact way to do that. Let's take a quick look at this next problem. Is this another tree problem? That appears to be another picky tree problem. Which is something I'm familiar with, but I'm not sure if I have enough time to figure it out in its entirety. So this basically has something to do with this structure, we are figuring out which subsegments are possible, sets of subsegments, and they kind of form this structure that's similar to the PQ tree. But then can we construct, given a PQ tree, can we construct a permutation that does not have any additional segments, is the question. I figure that it has to be some sort of dynamic programming, but let's try and figure this out. Okay. So not all these are possible, but that's probably all right. So the structure is the whole segment is partitioned into segments, into subsegments, and then they partition into subsegments. And depending on the type, if they are ordered, then we have all possible subsegments of that. And also we have everything that happens inside, right? But we cannot allow, we have these now. So how do we not allow that? We just have to make sure that this number is not an extreme, and that we can do just by flipping if it's necessary. So that's fine. But we also have this Q structure when no further subsegments are possible. So we cannot match any of that. So how do we ensure that? That's tricky. For example, if we have 3 subsegments, then we cannot do that because 2 of these are always going to be matched, right? Yes. If we have 4, then we could go for an order like 2, 4, 1, 3. And that works, I guess. If we have 5, however, if we have 5, and we have sort of a problem because we haven't placed 5 here, but we can place it. So what's the order? What's the correct order now? We cannot place 1 at the extreme. We can place 5 here, but what's the general idea? How do we order these segments? And also, if we have a small segment, then we are sort of bound to. We cannot kind of do that because the extreme is going to be on this side. Is this a problem? Probably not, right? So an order like this would work, and then yes, that's sort of what we're going for. No subsegment is possible. Yes, okay. If we have 2 elements, yes, we assume that it's not going to be adjacent to anything. How we're going to achieve that is we can just ensure that no external element is going to be adjacent. So the first element is not at the start, and the last element is not at the end, and that is always achievable. Okay. We have to write down a dynamic programming. Which is okay, that's a lot of states, but maybe it will work fast enough. That's a lot of states. Well, first of all, divide it by over 2 here, and then how do we proceed? So that's the type. Can we do that constructively? So with a Q permutation, with a Q node, we can subtract all the subsegments of these. Yes. That's not a lot of time. That's not a lot of time at all. How do we do this? If we have a Q node with K subsegments, we lose how many? Out of K over K plus 1 over 2, we lose all but 1, the whole segment. Do we have to account for that? Probably, yeah, and also K. So that is like K over K minus 1. K times K minus 1 over 2. Nope. It's something like this, right? And then we have to represent the the number of absent good segments as the sum of these numbers with the nesting condition. Great. Yeah, and K is at least 3 as well. At least 4. And that can be done with some kind of dynamic programming, but with 7 minutes there is no way I'm going to be finishing this. Yeah, so all the problems are really nice, I have to say. A is okay, right? You have to do some figuring out. I spent some time, but in the end it's really simple. B is just a quick observation to reduce the problem to a graph with very few edges, so you can do basically anything and find a shortest cycle in a very small graph. I believe I've discussed that, right? Because either you have three numbers with a common bit, and then you have a triangle, or you have, or for each bit there is at most one number with this bit set, and so there's only one edge in our graph that corresponds to that bit, and so there are at most 60 edges. And in that graph you can find the shortest cycle with BFS, as I did, and spend quite a lot of time as well. So here we have to figure out most of the information just by asking queries for like cells that are exactly 2 apart, because there is a palindromic path if they're equal, and then we have to kind of combine the information from the 2 halves with different parities from 2 different sets. And the way I did this was to basically try both cases and then figure out if the answer for any query differs between the 2 cases, and then ask this query. I'm not sure why this works, but we're guaranteed that you can sort of determine that unambiguously, and if that wasn't the case, if my solution wouldn't work, then it would be just impossible to determine. So yeah, I figured that should work. D is really nice, I love it. I kind of discussed that here. You start with a star, and then you can represent this like as follows. You basically comprise the answer from 2 different halves, one of which corresponds to the smallest half of the number that you want to represent, and then the larger half. And then you kind of go with this solution for the tree as well. But now you have to find the correct partition, and there is always a partition that so that the smallest part is at least the third of the whole tree. So that's cool. The problem is I spent most of the time, I would say an unreasonable amount of time on these 4 problems. Like had my troubles and all this kind of stuff, like 10 minutes, 15 minutes, half an hour, and then another 40 minutes. And then both of these problems look solvable. This is combinatorics with all these prefix function, the usual stuff. Basically, what you want to do is to, if you're conditioned with what are the prefixes and suffixes length that you have to match, then as long as, for example, if we only have one suffix, right, prefix, if they don't overlap, then it's really easy. You just have to count the probability of these characters matching and so on. And if they do overlap, then what you know is you can now consider these to be a random string, well, multiplied by a certain probability here, such that we have these prefix and suffix matching. And then you kind of have this nested recurrence, right? Because these can overlap as well, and so on. So you can kind of, I didn't write any formulas, but you can probably go on with that. And then if you have 2 pairs, of prefixes and suffixes, then you kind of do the same, except it's a bit more complicated. Maybe there is an easy way to figure this out, but I wasn't able to. And then in the problem F, well, if I read this from the start, I probably had better chances to get this problem done, because I've set a few problems based on this structure of consecutive subsegments. So I kind of know how that works, and I am able to reduce it to dynamic programming, but well, you know, I just didn't have enough time. Probably I would get it done, but anyway, so again, really like all the problems, really sort of mathematical contest. Would say no really involved data structures or anything, which isn't bad by any standard. I enjoyed all of these problems very much, so great job, problem setter, which was, I believe, Anton Trigup, right? Yes, really cool, really cool. I figure a lot of people have trouble solving this. So D, despite being like sort of simple, and the whole code is just like slightly over a page of code. But yeah, you don't see a lot of people solving it. Nice, nice. That was a good contest. And my performance is meh, but it's okay. Could do better, but a lot of people are struggling, so that's not too bad. Not too bad a place in the standings. All right, so that's probably all from me. I've explained something. If you want me to like explain it differently, or there is a problem, there is an issue with my notebook, which is massive. I cannot do very pretty explanations when I'm solving problems. So there you go. Yeah, so I'm checking out. Hope you enjoyed this and got at least something out of it. If you have anything to say, just leave stuff in the comments, and I'll answer that. If that was not answered in my previous videos, just if you're too many times. Right, so the contest is over, and now the screencast is over as well. All right, bye bye.